Hi everyone. Today I want to talk about characteristics of sine and cosine functions. Let's get right into it. Isn't this just the most beautiful thing you've ever seen? And the graph's pretty good too. That's funny. Okay, so here we have wow, what a way to start a video. So here we have the graph of f of x equals sine x, right? So I try to make it as big as humanly possible to fit in the window here, where we still start at 0. Now again, we are on the backdrop of the coordinate plane, and we are in radian measurement on our x-axis. And that's how we graph these things. Now clearly, I could still change this to our regular integer bases for the pi over 2, the pi, and they still would match up. It just looks a lot more fluid and a lot more correct when we put it on the backdrop of radian measurement, right? So for example, if I actually divided pi over 2, I'd get some actual value. And if we were on the coordinate plane, the graph would still look like the way it is. I just changed the representation of these values on the x-axis. So moving forward, when we talk about characteristics, we're talking about basic characteristics. And really, characteristics that we've done for years with regular functions like quadratics, linear functions, exponential, and then some of your higher level ones from Algebra 2, like rational functions, logarithmic, and so forth. So let's talk about these basic characteristics, which will help us later on with the graphing process. Here are a few of them. Now, there's a couple more, but we don't want to really get into those until we talk about transformations and graphing in general. So let's go ahead and answer these questions for our sine graph. Again, this is the parent function of sine x. There were no transformations, and you can tell because there's nothing added into this function. It's just plain old sine x. So let's talk about the domain. Domain is left to right. How far does it go on negative infinity, and how far does it go to positive infinity? Well, this function is continuous, which means that it will have all real numbers as its domain. So we represent that by negative infinity to positive infinity, okay? Or we could put the double R for all real numbers. Range. Well, remember that range is its lowest value to its highest value. Now we can actually see this on the graph. Our lowest value here is at -1 on the y-axis, right? So even though we don't actually touch at -1, that is our lowest point. It does go up to +1, and it won't go any higher than that, just like it doesn't go any lower than our -1 value. So the range is going to be -1 to 1. But when we talk about range values, since it actually does touch those values, we have to put brackets. And that's a terrible bracket. Let's move on. X-intercepts. Okay, this is where it gets kind of funky. Well, we can tell that there's kind of a lot of x-intercepts. Would we say that there is an infinite amount of x-intercepts? Yes, we would. So let's start with the x-intercept that we know is pretty clear, and that's at 0. So we're going to put that first. Our x-intercepts start at 0. Now, we can see clearly there's an x-intercept at pi and 2 pi. So what's really happening here? Our x-intercepts are going to continue in this pattern. If I were to shift this graph over so you can see more, we're going to have an x-intercept at 3 pi, 4 pi. If I were to go towards negative territory, I would have one at negative pi, -2 pi. So there has to be a way to represent that. Well, if we use the letter k as our variable, we can say that all multiples of pi will be an x-intercept. So we can say that pi times k, or pi k, will be our infinite world or infinite family of x-intercepts, because they never will end. So we can say pi k is going to be our multiples of x-intercepts. The y-intercept isn't so lucky though. There's only one, and that's going to be at 0, 0. Now we could put 0, and that would be fine. We can put 0, 0. That's totally fine as well. It doesn't matter either way for me. Maximum value. Okay, well, there's multiple maximum values because they happen often. When you think about maximum and minimum, you want to think in terms of x-intercepts because they happen a lot. So let's go ahead and see what our first max value is. The first max value I see is pi over 2. So let's go ahead and put that as pi over 2 as our first max value. Well, you can't really see the next one, but if I went to pi, 3 pi over 2, 2 pi, after that is going to give me my next value. So let's count. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. So what did I do from our first max to our second max? Well, I really added 4 pi, right? So every time we add this 4 pi multiple, we're going to get values that are giving us our max value. So our next one would be 9 pi over 2, and so on and so forth. I could also subtract our 4 pi on the other side to get that value too. So we can also use this value here for k. I can say any multiple of pi over 2k represents the max values because they are infinite, just like our x-intercepts. Minimum values will be the same as well. So our minimum values, and again, I kind of wrote all over the place, so let's just go here. The first minimum value we see is at 3 pi over 2. Well, if I continue that pattern along, I'm going to continue to get minimum values. There is another infinite family or infinite number of minimum values, just like x-intercepts and just like our maximum values. So how we're going to write that, we can start with our 3 pi over 2, right? And we can also say that it increases by our values of 4 pi. So 7 pi over 2, 11 pi over 2, and so on and so forth. So we can say that 3 pi over 2, which was our initial, which you can't see. I actually did write something. So let's say that we had 3 pi over 2, k. So every multiple of 3 pi over 2, positive or negative, is going to give us another minimum value. All right? And again, we're not going to see or ever look at the entire or a bigger graph of this. We really want to truncate this to just pieces of it so we can see it a little better. I don't know if we'll ever go more than 6 or 8 pi on one way or the other, but you can get the point where as long as you understand that there are infinite values of our minimum, maximum, and x-intercepts, we're looking good. Okay? Now, let's talk about the type. Now, type is kind of a generalized term. The type of function certainly is trigonometric. Now, we would say that for any type of function of its family, right? So when we talk about quadratics, things that are squared, they would be quadratic in type. Linear, exponential, so on and so forth. This is trigonometric in its very base. Now, I also want to make sure we understand that this is a continuous function. Continuous. When we start talking about continuity, when we start talking about either wholes or asymptotes or anything to that nature, discontinuity, this is not one of them, right? So when we have a trigonometric function, when it's sine or cosine specifically, we'll talk about the other 4 later on, but we also have a continuous function. Now, symmetry. This is really important for sine and cosine specifically. Take a look at what's happening at the origin. At the origin, we're kind of going diagonally through. That implies that this has odd symmetry. It has x-axis symmetry, which means odd symmetry. Now, think about it. If I were to take just this portion that we're looking at, the period from 0 to 2 pi, and I were to reflect it over the x-axis, I don't get exactly what I'm looking at, because this hump here would be that hump there. That is not exactly how that works. There is no y-axis symmetry here. Odd functions, however, have kind of like a diagonal symmetry, right? So the symmetry in sine functions will always be odd, and it's because of the way it crosses diagonally through the origin, okay? So that pretty much sums up our characteristics, at least basic characteristics of sine graphs. Now, one more note before we move to cosine. Let's star the things that will change when transformations occur. The domain will never change, so we're not going to star that. Actually, circle it because it's a little easier. The range will certainly change if we have amplitude differences, right? So obviously the amplitude here is 1 because we don't see a number. There's no coefficient of sine. But if I get numbers up there, it's going to be our vertical stretches, right? So that would certainly change the range of the function. Our x-intercepts will also change significantly when we have any kind of period change or any kind of shift left or right. Y-intercept, well, that might also change, right? Because when we have a phase shift, anything horizontally, that's going to shift the way that this works. Maxes and mins will also change. And I'm trying to circle it, but it's not working out so well. Maxes and mins will also change. The type does not, and the symmetry actually will not change either, because sinusoidal graphs, in terms of the sine x, doesn't change at all on the symmetry way. Okay, so let's go ahead and move forward and get cosine underway. Okay, you're back. Take a look at this orange function right here, cosine of x. Whew. And it works perfectly, so my head's just like right here, just making it happen. Okay, it's perfect. Let's talk about the characteristics. So as you can imagine, the characteristics are going to be pretty similar, right? So I've highlighted obviously from 0 to 2 pi, which is 1 period of this function. Clearly we have differences in terms of cosine because cosine starts at 1 if we're talking about its period start, right? The domain doesn't change. The domain is negative infinity to positive infinity. Okay, you can put the plus or not, doesn't matter to me. Range is also the same. Range is going to be bracket -1 to 1. X-intercepts here, though, they're certainly going to change a little bit, right? So our x-intercepts here, well, the first one here is pi over 2. Well, if you recall back from the sine function, what was our x-intercepts there? Well, it started at pi. So we can see that there's a difference already in the x-intercepts. So our x-intercepts here will start with pi over 2 on the positive side. The next one is 3 pi over 2. And so on and so forth. So we're going to be increasing by this other set of values of pi. So how can we write that? Again, we can say that it's going to have odd multiples of pi over 2. So 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. So we can say that it's any odd multiple, or we can just go ahead back and say that it's going to be values of pi over 2 times k when k is odd, right? So when we talk about these values, again, odd numbers, 1, 3, 5, 7, only works when k is odd values. So it's going to be a little bit different because it's like already kind of shifted over a little bit, right? So there's a lot in common with these two graphs. Let's talk about the y-intercept. The y-intercept is only 1. The y-intercept is at positive 1, or it's at the value 0, 1. Max values, well, we have maximum values at 1 when it's 0. We have a max value at 2 pi. So our maximums occur at 0, 2 pi, 4 pi, and any even multiple of pi. So we can say that our maximums will be any even multiple, or 2 pi times k when k is even, right? So 2, 4, 6, 8, and so on and so forth. Minimum values will be just opposite. Oh no, there it is, pi. I thought it was too low. So our minimum values, and again, I'm going to do a little arrow here, will be at pi and any multiple of pi. Right, so when we have this odd multiple of pi. So when there's any odd multiple of pi, we're going to have minimum values. So we can say it's pi, 3 pi, 5 pi. So pi times k when k is odd will be our odd multiples. And you can't say that so much, but you can hear me, so that's good, right? Of our minimum value. Next, other, or type. So again, the type is trigonometric. It is continuous. Okay. Now, the symmetry is what's important here, because the symmetry of cosine functions is even. And we can tell that it's even because even symmetry has y-axis reflection capabilities, right? So if I were to take this snippet and move over here and flip it, literally reflect it across the y-axis, it would be a mirror image, it'd be a perfect mirror image of itself. And that means that it's going to have even symmetry. Symmetry is one of the more important things, even though it seems pretty simple to understand, because it helps us recognize the differences between sine and cosine and any kind of transformations that occurred. So let's talk about the differences from cosine to sine. Domain's the same, range is the same. The intercepts go by a different pattern. The max and min go by a different pattern. Certainly the y-intercept is different, but we knew that from how the unit circle kind of worked out. And our symmetry is even on a cosine function. Let's finish up. 3 things to remember about this video. Number 1, basic characteristics are very important for all types of functions, any kind of function family we talk about. Specifically here, we're talking about trigonometric functions, obviously. But it's really important to understand the base characteristics so we can build off of that and start to transform them through graphing and other ways. Number 2, remember that some of these characteristics change through transformations, like I had just said. And then number 3, knowing function behavior. Now, when we talk about basic characteristics, this is the function behavior. What is its domain? What is its range? What are the general characteristics that it has before things occur to it? And because that's important for classifying general characteristics, transformations, and even graphing into the future. See you next time.